Today we are going to solve exercise 12 and in it we have to prove proposition 12.1.18 whose statement we may not remember. That's why I have the statement here. So it is that proposition which gives us convergence of those three metrics on Rn, L2, L1 and L infinity. It is that thing. But anyway, let's see the statement once more. Xk is a sequence in Rn because we have already seen it once, so we need not see everything in detail right now. So Xk is a sequence in Rn where k varies from m to infinity, and each vector Xk, because each element is coming from Rn, it's a sequence in Rn, so each element will be a vector, or each term of the sequence is a vector having n components. So Xk looks like this. And there is also another vector x in Rn. Then the following four statements are logically equivalent. If any one of them is true, then so are the others. The first one is that this sequence converges to x with respect to the metric dl2, and then convergence of that same sequence but with respect to the metric dl1 and then dl infinity. And these convergences are true if and only if each component of this xk converges to the corresponding component of x. And you know what that means already. So let's now prove this. So this is how we are starting the solution. By exercises 12.1.8 and 12.1.10, B implies A and A implies C. This may seem like an extraordinarily short argument. In fact, there is actually nothing here. It's as if we are just simply concluding something that we need to conclude. But let's go through the details and then you will understand that it looks big, but it's really not that complicated or anything very difficult or twisted. Let us prove that B implies A. So B implies A means we are going to assume B. So B is going to be our starting point. That means we are assuming that our sequence xk converges to x with respect to the metric dl1. Now what does this limit mean? It means that for any epsilon greater than 0, there exists an integer n greater than or equal to the starting index m of our sequence xk, such that the dl1 distance between xk and x is less than or equal to epsilon for all indices k greater than or equal to that n. This is just the definition of convergence that we have applied to this limit, this convergence. But now you recall the inequalities that we previously got, and in fact in exercise 12.1.8 we were asked to prove those inequalities. 12.1. One of those inequalities is this, that dl2 measures the distance between two vectors in Rn which is less than or equal to the distance between them as measured by dl1. And actually this is true always. So this will happen for all possible cases, but in particular for those cases that are greater than or equal to n also this will happen. So if these quantities are less than or equal to epsilon and this is less than or equal to this, automatically this would be less than or equal to epsilon for all k greater than or equal to n. But what does that mean? That just simply means that for any epsilon you have found an n for which this inequality is true. The dl2 distance between xk and x is at most epsilon, less than or equal to epsilon. And that's why the limit of xk is also x with respect to the metric dl2, and that is just A. So you see that actually it's quite easy. And similarly, A also implies C. So we are not going to show these things. Instead, now next what we are going to do is somehow we are going to bring in D, because statement D is also there, and then let's see what happens. Actually, before we get to the statement D, we want to prove that C implies B, because in the beginning we concluded straight away that B implies A and A implies C. Now if we can prove that C implies B, then the equivalence between A, B and C is already there, and then we can handle D. So that's what now we are going to do. We will show now that C implies B. So we assume C, that is we assume this, that our sequence xk converges to x with respect to the metric dl infinity, the sup norm metric. This, however, I am making a part of the solution because there is a little, I won't say it's a twist, but the epsilon value has to be chosen a little carefully. That is why. So what does this mean? It means that for usual meaning, for any epsilon greater than 0, there exists an integer n greater than or equal to m such that the dl infinity distance between xk, this k should be within brackets, otherwise the meaning changes. The dl infinity distance between xk and x is less than or equal to epsilon divided by n. You will realize why we made this choice of taking epsilon divided by n, and recall that n is that n that we have in Rn for all k greater than or equal to n. So what do we get from these inequalities? If you multiply both sides by n, because n is a positive integer, so you will get n times dl infinity distance between xk and x is less than or equal to epsilon for all k greater than or equal to n. And we need this n because we want to relate dl infinity to dl1. If you go back to the inequalities 12.1 and 12.2, there is no direct relationship between dl infinity and dl1. However, you can combine those two inequalities and get this fact, that dl1 distance is less than or equal to n times dl infinity distance. You will have to think a little, you have to involve that dl2 because that is related to these two metrics. But using those inequalities, this is a consequence. So I am not going to say anything more on this. It's a very simple matter. You just go and see how dl1 is less than or equal to n times dl infinity. And this, of course, again is true for all k greater than or equal to m. In particular, for this type of case also this is true. So n times dl infinity is less than or equal to epsilon, and dl1 is less than or equal to n times dl infinity for that type of case. That is why dl1 would be less than or equal to epsilon. That's it for all k greater than or equal to n. So that just simply means that our sequence xk converges to x now with respect to the dl1 metric, little l1 metric. And that is our part B. So C implies B. So what did we initially conclude? That B implies A and A implies C. Now we have proved that C implies B. That is why these three things, these three statements are logically equivalent. B is true if and only if A is true, if and only if C is true. And now we will go to D. So next, what we do next, we assume A. We go back to the statement A, which involves our metric dl2. So that means now our sequence converges to x with respect to dl2. Okay, actually now we can consider any metric here in place of dl2 because we have just now shown that A, B and C are equivalent to one another. But we chose dl2, okay, because it's convenient, at least to me. So now next what we do, we now want to prove D, statement D. So we fix a J, and what is it that we want to prove now? We want to prove that this sequence of real numbers, not n-dimensional vectors, this sequence of real numbers is having this k as its index. So as k changes, the real numbers change, and here we are looking at a single real number that converges to xj, the jth component of that vector x. So from this limit, what do we get? For any epsilon greater than 0, usual stuff, there exists an integer m If you want, you can call it n also, no problem. Greater than or equal to m such that the DL2 distance between xk and x is less than or equal to epsilon for all k greater than or equal to m. Nothing unusual. And here we are just taking epsilon as epsilon, no epsilon divided by n or anything. But then we also have this. So what we do, we consider the square of the distance between the real numbers xjk and xj, which is this. That of course is less than or equal to this sum, where instead of simply having that j, we have all the i's, where I varies from 1 to n. And this is less than or equal to this because all the terms in this sum are non-negative real numbers. And this is one of them. Okay. And you already know, we have already gone through similar arguments before, why this is true. But this sum is the square of the DL2 distance between xk and x. So this square is less than or equal to this square. But already this is less than or equal to epsilon for this type of case. So this square would be less than or equal to epsilon square for all k greater than or equal to n. That means this square is less than or equal to epsilon square for all such case. Because we are dealing with non-negative quantities, this absolute difference is a non-negative real number and epsilon anyway is positive. So you can lift square from both sides and that will give you this. That this distance between xjk and xj real numbers is less than or equal to epsilon for all k greater than or equal to n. But then this sequence of real numbers xjk where k changes from m to infinity converges to the real number xj, and that's what we wanted to show. So that means A implies D, and now we will prove that D implies A. Conversely, we assume D. That means for each such I, we have this limit. That means here we are looking at n number of sequences of real numbers, each one is convergent, and the ith sequence converges to xi. The ith sequence has this general term xi k. Okay, should not say to the power k because k is superscript here, not exponent. So for each such I and any epsilon greater than 0, if we write what this limit means, then there exists an integer in I. Because this integer is for that specific I, so we write in I to show the dependence of n on I. Or if you want, you can write n within round brackets I. That n is a function of I, but this is also okay. Greater than or equal to m such that the distance between this kth term of the sequence xik, that is xik and xi, because these are real numbers, the distance is your ordinary absolute value distance. It is less than or equal to, but here again we do a little trick. Instead of simply taking epsilon, we take epsilon divided by square root of n. We will see why this is needed. For all k greater than or equal to that ni. Now note that here we have n number of integers ni, n1, n2, n3 up to nn, and that's a finite number, so there will be a maximum of them. Let that maximum be n. Now if I choose k to be an integer greater than or equal to that maximum n, then k is greater than or equal to each ni, and so for such a k, all these inequalities are going to be true. That means for all I simultaneously. Do not get confused, okay? I varies from 1 to n, but k varies from m to infinity. These are two different variables. So for a single value of I, we are looking at how the terms of that sequence behave as you change k. All right. So now where are we? Now for any such k greater than or equal to n, what is our aim? Our aim is to go to the statement A, which involves the metric dl2. So let's see what happens now with the dl2 distance between xk and x. Here you do not see any I immediately, because here all the i's are being taken into account simultaneously, because unlike those things, these are n-dimensional vectors. So by definition, this is just this square root of sum of squares of you already know. So now what can we say about this sum now that we have these inequalities? Let's see. So if we now replace each term of this sum by, because here we don't have just these terms, but they are squares. So we replace each one of them by the square of epsilon divided by square root of n. Then we are likely writing more. That is why this thing is less than or equal to this. Actually, you should be a little careful when you replace things like this and write an inequality. Do not forget that it's not simply the sum but square root of sum. However, ultimately we do get to that inequality. There are some intermediate steps. I am not going to discuss about them. You already should know these things. Alright. So now all the terms of the sum have become equal to the square of epsilon divided by square root of n, which is just epsilon square divided by n. So how many terms are there in this sum? N number of terms, and each term is epsilon square divided by n. So their sum would be n times epsilon square divided by n, or epsilon square. And already we have a square root outside, so this is epsilon. And that way, for all k greater than or equal to n, the dl2 distance between xk and x is less than or equal to epsilon. That means for that epsilon, we have found an integer n for which these things are happening. And that is why xk converges to x with respect to the metric dl2. And that's how our d also implies a. So that means now we have finally proved that these four statements are all logically equivalent to one another. If any one of them is true, then the other three are also true. And if any one of them is false, then so are the other three. So that completes the solution to this exercise. And let's just end this video here itself. There are other exercises, but we cannot do more than one or two exercises in one video. I mean, I can of course go on and on, but the video will be extremely long. And long videos usually are a little boring. So see you next week with more exercises and their solutions. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.